dash is at the end of the pulse, and the solid, the blue line, is at the detector. And okay, so these kind of have the same shape, but clearly the width is different. The cosine squared theta changes by 14%. These actually look pretty good, right? Those match pretty well in that case, but this one is fairly dramatically different. And these are from different, let's see, what are these? These are a specific initial vibrational state and different wavelengths, okay? This one also, fairly dramatic difference. Okay. So the point is, that just because you might measure this final distribution, say the blue one, it may not be safe to assume that that was the distribution when the thing broke, okay? Because this dashed line is the closest we can come to that distribution when it broke. So axial recoil looks like it might have, there should be some caveats. Now, a thing to keep in mind, the dissociation energy of these things is on the order of an EV, okay? And you might be creating, I mean, in this case, you can see there's lots of angular momentum in that wave function. That's how you get so many lobes. So that means that the radial kinetic energy isn't so large compared to the rotational kinetic energy, okay? Which was the underlying assumption of axial recoil. So it's not necessarily a surprise here. So the things that Paul was talking about, Coulomb explosion imaging, where you go up onto this repulsive Coulomb potential, you have this whopping big radial kinetic energy compared to the rotational energy. Axial recoil probably doesn't work too bad there because it will fly apart before it can rotate, okay? The caution here is, just remember that when you're doing strong field and you're doing dissociation, that may not be true, okay? And it may be dramatically not true. It's getting late, I won't talk about this one. The key point is that including rotation is actually fairly important if you want to make quantitative predictions compared with the experiment, okay? Because experiment measures angular distributions. So you need to include the angular degrees of freedom to produce predictions. We talked about these things. One thing is that we check things only for H2 plus potentials, okay? It will be interesting at some level to check what other kind of characteristic shapes of potentials will do. But again, I expect this is the ratio of radial kinetic energy to the rotational kinetic energy that will matter, okay? And I guess I will stop there. Thank you.
Thank you so much. We have time for questions, comments. Yeah.
So, seeing the difference in the axial recoil and the exact,
Yeah.
there's no real way to do the experiments better in that case, is there? Or
No, that's...
So what's the, is it just a caveat when you're doing the interpretation, or is there a way to?
Yeah, I would say it's a caution to use the language more carefully,
Okay.
right? I mean, once you measure the momentum distribution in infinity, unless you can argue that, again, the radial kinetic energy is much larger than the rotational one, then all you can say, this is what it is at infinity, right? I just wouldn't say, that's what it was when it broke.
Yeah.
Okay?
Yeah, sure.
So I would like to hear your point of view. If now you have an aligned example of molecule.
That.
Okay. We planned this.
No, we asked this question too, because in fact, there's a lot of interest in aligning molecules, and mostly people think about ionizing those things. So we said, okay, what happens when you dissociate them? Well, if you align it really well in some direction, then, and you dissociate it, if axial recoil is true, it should just go that direction, right? And that seems like a good case to check. And again, the side monitors might be better to see this. You can see, so theta naught is the angle between the alignment angle of the molecules and the laser polarization, okay? So this angle is theta naught. So the molecules are aligned with a degree of alignment of about 0.9, which is pretty good alignment, okay? Around this angle to the laser polarization. So if axial recoil is true, then the angle they dissociate to which is plotted here, should just be equal to the initial angle. So in other words, this peak should fall along the line, theta k equals theta naught. And you can see that for low angles near the polarization, that's more or less true. But you can especially see on the side monitors that as the alignment angle approaches really about pi over 4, that's no longer true. Okay? That's no longer true. That the peak of the distribution is really sort of along there. It just kind of goes straight across. Yeah.
Or I think that answers this question about what can an experimentalist do, because this is what, in fact, one does, is invoke the one other piece of information that you have, which is energy conservation.
Right.
And if you discover that there is kinetic energy that's kind of missing, in other words, you can't account for the energy of the recoil just by looking at the angles that things appear, then it's because you put energy into rotational motion. So you see it directly there. If I'm understanding what the y-axis is.
Yeah, I mean the y-axis is the angle of the fragments at infinity. So integrated over everything else, energy and everything else.
How would this, so this was for dissociation, so if now we had breakup, it would be better, right? In the sense that you would have less effect of this exact treatment of the rotation.
Sorry, say that again. This is dissociation, right?
Yes, this is dissociation.
Yeah.
Now you had ionization.
Okay, so if you're going up to, say, a repulsive
Yeah,
Coulomb
then-
curve and you have a lot more radiokinetic energy.
Then you would expect it to be accurate to use the...
Yeah, although in this case, I still don't expect it to go all the way down, because if it's perfect down there, there is no transition, right? That's one thing that we didn't really get into, is that H2 plus, if you only have 1s sigma g and 2p sigma u, it only has parallel transitions. And so if it were perfectly aligned, if it were no rotation included, and you align this thing perpendicular to the polarization, you should see nothing at all, because there is no transition dipole moment then. So the fact that you see something even over there, when it's aligned perpendicular, that contradicts that model. And of course, the interpretation, I think, is just simply that we don't have a perfect alignment, we have a distribution, so the wings of our angular distribution are getting dissociated even when the center's at pi over 2, even when the center's at 90 degrees. Yeah.
If you look at angle not at infinity, but at some finite distance, can you just infer the amount of rotational energy?
Sure, and that was a plot that I asked my student to make, is just take one of these guys and make the movie and see if you can watch it curve out to infinity. That would be fun. But I don't think he's made that one yet. Yeah.
The Born-Oppenheimer potential you show, it seems that by one photon you can dissociate the molecule.
Right.
But you have another Oppenheimer potential after that. It seems that by multi-photon you go over there and still you are in the bonding, not dissociated.
Oh, you're talking, okay.
It seems a little bit counterintuitive. By one
Let's see.
photon you dissociate, but by multi-photon you still in the...
So you're talking about getting trapped up there, for instance. Okay. So it sounds strange to you that you can dissociate with one photon,
Yeah,
but you can put more energy in and not dissociate.
Yeah.
Yeah, I mean, you say it that way, it probably does sound kind of counterintuitive. But I think when you look at this, it's not too surprising, right? Because if you go from one well to another, which is not very likely here, by the way.
Right.
Because, again, if you think Frank Condon, you're going to go straight up, and that puts it up here on that curve, and that's definitely going to dissociate. And I can tell you from the calculations, we don't get very much that sticks in there. Because we've included these in the calculations. And what you see is really high energy dissociation on those channels. But you might be able to find a molecule where that can happen. Yeah. Well, you're just pumping the energy into the internal excitation, right?
Well, if you start, I guess, from just below the ionization level, you might get there, right?
Oh, you mean if you start out here in this high vibrational state?
Yeah,
Yeah, you probably have some chance.
yeah.
The problem is that state is like 0.002% in the initial distribution.
Right.
Yeah. So there just isn't much of it to contribute. If you could prepare it that way,
Right.
but that's something folks aren't able to do so well these days.
You have to control power.
Exactly. Yeah.
Are there further questions or comments? If not, thanks again so much.